Okay, next is here we have the AX3E1 type. So here we have 4 electron pairs. So this assumes the tetrahedral electron pair geometry, but in this case we only have 3 terminal atoms. So we have AX3 and then we have 1 lone pair. So here this is a molecular geometry of triangular pyramidal. So again we have a triangle, 4 triangles, and we have the pyramid here. So this is not the same case with the tetrahedral. Okay, next is we have AX2E2. So here we have the molecular geometry bent. So we have X, A, and X here. So we will see these atoms in the microscope. Okay, but we do not see these electrons. So still, since we have 4 electron pairs around the central atom A, so this has the tetrahedral electron pair geometry as well. So next is we have other shapes. So these 3 are derived from the triangular bipyramidal shape. Okay, so we have AX5E0, and then here we replace the one terminal atom to be one lone pair. So we have the seesaw. Okay, so if you will invert this, okay, so this one, so this is the center of the seesaw, and then this and these terminal atoms here are the ones wherein you can sit in the seesaw. So this is it. You have to have an active imagination for this one. And then here we have AX. This must be AX3E2. So this is wrong. Okay, so in the AX3E2, so this is T-shape. And here, if we have AX2E3, so this assumes the linear shape. Okay, so the electron pair geometry of these 3 molecules are all triangular bipyramidal since we have 5 electron pairs surrounding the central atom, but the molecular geometries are different. And then here, for the last 2, we have octahedral electron pair geometry since we have 6 electron pairs surrounding the central atom. So this time, or in this case, we have AX5E1. So we have a square pyramidal molecular geometry. And then this one is a square planar molecular geometry. So what if we have AX3E3? AX3E3 is similar with this one, so we have T-shape. And then AX2E4 is similar with this one, but we have 4 here. So we have linear shape. Okay. Let's have a problem. What are the electron pair and molecular geometries of the following? So again, you need to draw the Lewis structures first and then determine the bonding pairs and the lone pairs around the central atom before you could predict the electron pair and the molecular geometries of these molecules. So again, kindly do this first. Okay, so let's see the answers. So SEF6 or selenium hexafluoride, so this has this shape. So this one is octahedral since we have 6 electron pairs around it. and we do not have any lone pair, so this means that it has the same molecular geometry as well. Next is IF3. So IF3 has this Lewis structure. So as we can see, this is AX3E2. AX3E2 has triangular bipyramidal electron pair geometry, and we have T-shaped molecular geometry. Next, we have TEF4. So here, this is the one, and the type of the molecule is AX4E1 or AX4E. So the electron pair geometry here is triangular bipyramidal, and the molecular geometry is seesaw. Okay, please take note that in this two, even though I draw this as like this and this one, so they are not really the correct Lewis structure for this one, since this one must be T-shaped. Okay, so we cannot see here that this is T-shaped, and then this one should be seesaw. Okay, so this means that Lewis structures could be deceiving. So that means that not all the Lewis structures that we can draw is the same as what is existing in the real life. Okay, so we need this chapter for visualizing the molecular structures. So last is we have XCF5 plus. So here we have this one. Okay, so we have 6 electron pairs around Xe, and this is octahedral. So the type of this one is AX5E1 or AX5E. So the molecular geometry here is square pyramidal. Okay, so much for VSEPR theory. We'll move on now to another aspect of visualizing molecules. So this time, this is the interaction between molecules. Okay, so from the geometry of the molecule, so if we can now draw the proper Lewis structure for molecules, we can apply the dimensional strategies to check the polarity. So again, we all know how to determine the polarity of a bond. For example, this one, HO. So H is the partially positive end of the bond. O here is the partially negative end of the bond. And then, as we can see, all the electronegativity point towards the O. So this means that it has a net dipole. So this means that water molecule is polar. Here we have the bond. Okay, CF. We have 4 CF bonds. And this time, they all cancel out. So if you will plot this in a 3-dimensional space, you will see that these polarities or these electronegativities here will just cancel out. So it has no net dipole, so that means this is non-polar. While CHF3 is polar, so it has a net dipole towards the fluorine atoms. Okay, so we need to check first the polarity before we can proceed with the discussion of the covalent, non-covalent interactions. Okay, so I will do the last discussion on the next video.